Okay, step number 6 of plotting the root locus. And this step you will only going to use if you have some poles that are complex conjugate. If you don't have any pole that is complex conjugate, you don't have to use this step. So only if you have poles that are complex conjugate. And for those poles, we need to figure out what will be the angle of departure of the root locus from those poles. Remember, we are using angle of departure. Why? Because the root locus starts at poles and ends at zeros. And again, if you have a complex conjugate zeros, then you still have to repeat this step, because then root locus will be arriving at zeros. Instead of departing from the poles, it will be arriving at zero. So you want to know what will be the angle of arrival if it is 0 of the root locus, one section of the root locus, or if it is a pole, what will be the angle of departure of the root locus from the pole. Now remember, anytime you have complex conjugate poles, it comes in a pair, you already know. You only have to do it for one of them, because remember, it is symmetric. So for the other pole or zeros, the conjugate of that is going to be exactly the same, only in the opposite direction. So how do we do that? Basically, the idea is that we use the original angle criteria. That is, angle of Fs is equal to 180 plus minus k 360 degrees. And remember, Fs was product of all the zeros divided by product of all the poles. So angle, when you're calculating angles from that fraction, is going to be angle of each zero minus angle associated with each pole from any point S on the root locus, and that should be equal to plus minus 180 plus k 360 degrees. So let's look at this example. What we do basically, if we do have some pole, let's say I have a pole over here and I will have a pole over here, complex conjugate, we choose a point extremely close to the pole. One pole, just take one pole. We choose a point extremely close to that pole such that we assume it is the pole. And then from each of the other poles and each of the zeros, we measure the angle that it makes if we draw a line or a vector from each of the pole to the pole under consideration, where we are taking in a point extremely close to the pole, that is the complex conjugate, the complex pole. We draw a vector from each pole, and then we measure what is the angle of that vector with respect to x-axis counterclockwise. And likewise, we draw a vector from each zero, and then we measure the angle that it makes with respect to x-axis. So when we have that angle, then we can use this equation, angle of each zero to that point from from the pole, from any point, and angle of each pole up to that point from each of the pole. So this S basically is right here, S1, what I'm taking. It's like a point very close to your pole under consideration. And the angle to S1 from the pole under consideration, we take it as, any angle. I'm calling it theta 2 over here, let's say theta 2. So now you have how many angles? You have theta 1 if you have this pole, if you have this pole, theta 1, this pole, theta 3, and from this pole to the point very close to this, theta 2. And our job is to find theta 2, because that theta 2 is going to tell us what is the angle of departure of one section of the root locus from this pole. So draw vectors S plus P3, S1 plus P2, S1 plus P1. This is the point S1. And then we add up all the angles, and they should be equal to 180 degrees. So we know the angle over here is, let's say, 90 degrees. That is going from P1 to that point approximately, because P1 and this, this is complex conjugate. So that's 90 degrees. If we know what the value of theta 3 is, then it's very easy to find the theta 3 value. we'll do an example and with the numbers and do that. Then if we know the theta 3 value, then we can figure out what is theta 2 value. Okay, so this will be step 2. Again, we're gonna solve the whole problem, and this step will be part of the problem.